Hello and welcome to this tutorial covering amplifier protection circuits and typical faults. Probably one of the most common questions that I receive either via the messaging or directly via email is really about amplifier protection circuits and how they operate and the different types of circuits. And probably one of the most difficult areas is trying to determine if you have an issue with the protection circuit or the amplifier itself. And on previous sort of audio tutorials that I've put on more recently, I've sort of just touched on that, but I just felt that it was time now to do a dedicated tutorial which really gives you a lot of more information. So as many of the tutorials that I do, I'm just going to give you the overview with regard to the different types of circuits and how they've been implemented, but also as well, which is really critical, is that insight which is based on day-to-day repairs of audio amplifiers and the realistic and true faults which occur and how you can look for them and actually determine where the issue lies. If you go back in time and we look towards some of the earlier British amplifier designs, and I'm thinking maybe for example like A&R Cambridge, say an A60, the early amplifiers didn't have any sort of electronics sort of protection systems for the internal operation of the amplifier or for the speaker protection. The only thing that they had was fuses, and you've seen on previous repair videos often what you will have is a internal fuse, and there'll be one for the left channel or for the right channel, and these protection fuses are typically rated at about 1.6 amps for a conventional amplifier, maybe up to 40 to 60 watts, and the fuses are fast blow, and that means that in the event of a high current surge or high current demand, and sometimes it doesn't mean there's a fault, it could just be, when the amplifier is first powered up, you can get an inrush of current, and of course the principle here is that the fuses operate and break, the link inside breaks, fuse wire burns, and disconnects the flow of current, and then protecting either the amplifier internally or protecting the expensive speakers. And really that was what you saw on very, very early designs. But if you move forward in time, what you started to see then were new circuit designs which had protection circuits. So you will always have protection fuses for the power, so these are normally time delay associated with the power supply, but for the output protection for the speakers, then electronic circuits were designed, and you started to see that on a number of amplifiers. Now, for those types of amplifiers, the majority of them will have what we term as an output protection relay, a speaker protection relay. And these speaker protection relays can be for the speakers, but you may also see protection relays inside of amplifiers associated with the power supply. And what I'm referring to here is, in some of the repair videos, I describe something called a startup relay. And what a startup relay is, like a speaker protection relay, it is an electromechanical device, as you can see from the presentation along with this audio tutorial. And the purpose of the device in the case of the startup relay is that normally the control circuit, and that could be a microprocessor or it could be an analog type circuit, would operate, and then it would then switch on the power relay, the contacts would then make, and then it would then provide power then to the large power transformer. In the case of a speaker protection relay, then it's the same principle, it's the same device, and the intention there is that when the amplifier is working correctly, then the speaker protection relay will energize and it will make a set of contacts, providing the current flow then to the respective speakers. In the event of a failure, and maybe the amplifier detects an issue, maybe it could be high DC on the output terminals, or maybe a short circuit from the speaker wires or even the speaker coil, the protection circuit will operate and it will de-energize the relay. Now when you look at the video, what I've put in there is really an overview of what this speaker protection relay looks like. And I refer to something called form factors, and what that means is that each type of relay has a particular design. Alright, so what I'm referring to here, it's physical size and package, but also the pinouts. So this is the arrangement of the pins that solder into the board, and some relays on some amplifiers you may even find that they're mounted in some form of cradle or socket with a clamp mechanism so they can be easily changed. When I refer to electromechanical, you can see in the video a breakdown or exploded view of what a relay looks like. And what it is that you have a coil, normally with an iron core, and there is an armature at the top. So when we apply voltage and current flows through the coil, the iron core then will create a magnetic field, and then in turn it will then magnetize and it will pull down the armature. And then what you will then see is a movement. So this is a mechanical movement as the armature then pulls down, and normally there's a spring mechanism which will return it back to its original state when power is disconnected, and the internal contacts then change over. And these relays are designed to operate millions of times, and depending on the type of relay, we often use another terminology related to the switching mechanism or to the number of pins on the actual terminals. So you again, when you look at the video, you can see examples when I use SPST, SPDT, DPST and DPDT. And you say, well, what does that mean? Well, what it's referring to are the contacts within the relay. So when we talk about SPST, what we're saying here is it is a single pole, single throw relay, or a single pole double throw relay, and more commonly in the area of speaker protection relays, it could be a double pole, double throw relay. And the switching contacts, when you look at data sheets, talk about something called the normally open contact, a common, and a normally closed contact. And what that means is when the relay is depowered, the normally open contact is open. So this is the contact which closes only when the relay is energized. The common, in the case of a speaker protection relay, is where the left and right channel audio connects directly then to the common terminal, and this is the terminal which will move when the relay energizes between the normally open and the normally closed. So things to consider when you're looking to replace or to purchase new relays. The first thing is that you need to select the correct form factor, as I said, but also you need to look at the coil voltage. And for audio amplifiers, and taking into consideration modern amplifiers, there's normally 3 voltage types. For the control side, so this is maybe where it's been operated maybe from a microprocessor via some form of switching circuit, you may find that the coil is 5 volts DC operated. Or you may find a speaker protection relay or even a startup relay would be rated at 12 volts DC, and even more common, the relay is rated at 24 volts DC. Okay, not an AC relay, a DC relay. Now, there's also, when you look at the electronic schematics, often what you'll always see is a diode, and you see this diode connected really across the plus and minus terminals of the DC relay coil, and you may wonder, what's the purpose of that diode? Why is it there? And the reason why it is there is that if you have an electromagnetic coil and you remove the power, what happens is you generate a high, what we call an electromotive force, okay, and back EMF. And this back EMF can be considerable. So what they do is they put a diode across the coil terminals of the relay so that when it de-energizes, the diode then conducts, effectively nulling the back EMF. And that diode is critically important. Don't ever remove it, because if you do, then that back EMF would then go into the switching circuit of the amplifier and then would destroy it. If you're going to test one of the relays maybe with a bench power supply, also be aware of that. If you're just using test clips and you just disconnect them, then that's fine. But if you're going to be turning on and off your power supply to operate the relay, then you will need to put a diode, and this could be just a straightforward signal diode like a 1N4148 diode across there, and the cathode of the diode connects to the positive terminal of the relay, and then the anode then connects to the negative terminal, but it has to be installed then. The other thing that you need to consider, and it's more generic in some cases, right, and this is what we term as the resistance of the coil. Okay, so any coil will have a resistance. In most cases you can just replace the relay with a common form factor, the particular voltage for the coil, and a nominal resistance. But there are some relays, and again depending on the amplifier design, and I'll probably use an example like a Cambridge Azure range, say 640 series, 540 series and the 550. They use a particular make and model of relay, and through experience it seems sensitive with regard to what the coil resistance is. So when you look at the repair videos, you will see that I'm always referring back to the manufacturer's original relay, and then that's what is then installed then. The other important thing is the switching current, and normally on the datasheet it will tell you, but this information is always written on the relay itself. So if it was say a startup relay where you only have to apply AC to a power transformer, it would be very common then that the relay would be a single pole single throw relay, and that contact rating could well be 10 amps. If it's a speaker protection relay, you may find that it's a double pole double throw relay, and the switching contacts then are rated maybe at a nominal 5 amps. But remember, we're talking about 5 amps for a domestic hi-fi amplifier. If you're getting into the area of power amplifiers, where the power output may be in kilowatts, it would not be unusual to find even higher current rated relays, maybe even 20 amps, and their form factor or their design is very much different. If you look on the video again, you'll see that I've put a photograph of 2 relays which have been removed from an amplifier, and they just lied on the back of the amplifier board. And I put an arrow on there, and what I'm pointing to are these switching contacts. So you can see this armature that I referred to, you can see the common contact which moves, and those relays there are single pole single throw, because I can't see 2 sets of contacts. Now what happens is, over time, those contacts, like any mechanical switch, and you could think of a conventional light switch that you switch on and off, as it operates thousands of times, as the contact makes the voltage and the current, it produces an arcing, and then over time the contact can become pitted or worn. Also as well, the relay will start to oxidize. Now some relays, as you can see on the different relay types, are transparent and you can see through them, and those relays are not sealed as such, the same as the example that I'm showing you on the 2 relays that were removed. When I say they're not sealed, it's not a vacuum inside, so you have air in there, oxygen in there, and electricity and oxygen over time creates this oxidization on the relay contacts. And normally if you take the lid off them or the top cap off them, you can see the contacts and they're blackened, and then what you can do then is to start to clean them and to remove that oxide and try and restore them. But if the contacts are, sort of pitted and the contacts are worn, then the only thing you can then do is to replace the relay. But if the relays are sealed, then typically you'll get a little bit more longevity from that relay type, because it's a vacuum seal inside, you can't remove the top, and it's just then to provide additional life. Now concerning the types of contacts, in, I would say, audiophile type amplifiers, normally you will have gold plated speaker terminals, and it would not be uncommon again then to have switching contacts for a high quality relay, which would also have a gold coating on there to offer the minimal resistance associated with those switching contacts. Now what's the issue if these contacts wear, or for example they become oxidized? Well, because it's a switch contact, it should offer the minimum resistance to electrical current flow possible. When they become oxidized, they also start to become resistant or intermittent. The problem there, and we think about the low level signals, and remember these relays can also be on the input switching side of the amplifier, not just on the speaker protection output. Or it may be a startup relay again which is worn and you have intermittent startup issues. For speaker protection relays, you may hear low level distortion. You may also pick up that sometimes the amplifier loses the connection maybe to the left or right channel, and literally removing the top comer from the amplifier and then just giving the relay a tap often will restore it, and that tells you that those contacts need to be cleaned or the relay then replaced. The next example what I want to give you is really a change in design. So we moved from amplifiers which had no form of speaker protection circuit at all, and I'm going to use this example here, which is a Cambridge A3i speaker protection circuit, and it also shows the power supply. Now I appreciate for many of you who are listening to these audio tutorials, you may not be trained in electronics and you may not be trained to understand what this circuit schematic is doing. So I'm not going to go in depth in here. I'm just going to give a high level overview and just pinpoint a number of things which go directly into the operation of these circuits. Now, I spoke previously about speaker protection circuit, but amplifiers more commonly than not don't just protect the speakers. You may also have other internal mechanisms or internal circuits which are looking at other areas. So this example, and this is quite an old amplifier, more than 30 years old, and on the left hand side I can see over temperature protection. Now what is happening here is, and it's very common in these types of design, you would have a transistor, and they are using the silicon junction of the transistor, which is highly sensitive to temperature change, and what it's doing is it is monitoring the temperature of the heatsink where the power transistors are mounted, and in turn when those transistors run too hot for whatever reason, then the over temperature detection circuit would then operate, and then normally what will happen is it will then de-energize, in this condition, the output speaker protection relay. You can also see as well, you see DC output protection as well. So these two transistors which are shown for each channel, what they're monitoring is the DC offset coming across the speaker terminals. So again, if there was an issue either with the voltage input stage of the amplifier, the driver or power output stage, you may see a positive or negative high DC voltage which potentially could go across the speaker terminals. So what this circuit is doing is it's monitoring that voltage, and it should be as low as possible, order of a few millivolts. But if it is high, then that voltage would be sufficient to turn on the transistors, then they would then conduct. On the right hand side you can see RLA, and this is referring to the relay. Okay, so the relay in the case of the Cambridge A3i is a 24 volt relay, double pole double throw or double pole single throw, doesn't matter, you just snip off the additional two non-used switching contacts, and that circuit there is used to switch the relay coil. You've also got a switch which is at the front of the amplifier where you can just mute, and all that they've done is they've wired a series in series so that when you're operating it just simply breaks the connection and the relay then de-energizes. Now it refers to something called time delay and relay latching. So these speaker protection circuits have a timer. Now how this is formed in this type of design is that you use a resistor and a capacitor, and that forms what we call an RC network. So if you have a resistor in series with the capacitor, the resistance will reduce the amount of current flow over time, which means that the capacitor will charge up at a slower rate. So when they select the resistance and the capacitance value, the calculation is simply time equals C, the capacitance value, timed by the resistance, will give you the time period then that it will take the capacitor to charge. Typically here it would be 5 seconds. Now what's the issue that can happen? Well, it's not uncommon over time, because you rely on a capacitor to form part of that timing circuit, that capacitor starts to dry out and it's no longer able to operate as a capacitor, hold a charge, and you could find that either A, the capacitor, because the value is dropped, charges up very, very quickly, so maybe the timing circuit sort of switches on almost instantaneously, or the switching circuit doesn't operate at all because the capacitor is no longer a capacitor, so there's no charging. So in this case the FET cannot switch on and then energize the protection relay. Now if I think about NAD, and I think about the NAD, say C370, with that particular design you see a vertical board which is the protection circuit, and the electrolytic capacitor which is used for this timing circuit is mounted on that board and is very, very close to a power resistor. And you might have seen it on one of the repair videos that I put together with the tutorial. This is a common issue where the capacitor dries up over time, accelerated life in terms of deterioration, and companies do offer repair kits, but normally it's best practice to sort of recap that kind of amplifier. So really 3 circuits there, right? So we have the over temperature protection, we have the DC offset protection, and then finally the circuit on the right hand side where you can see the charging circuit then used to provide the time delay. And when you turn off the amplifier, the relay would be instantaneous, it would de-energize immediately, And the reason why we do that is we're just waiting for stabilization of the DC power supply. So all circuits then are operating at nominal voltage and all current is good. If you didn't have the speaker protection relay and the delay, then when you power up, you would hear through the speakers this charging effect. And often on early amplifiers, you had to reduce the volume control to try and mitigate that. The next thing I'm going to show you is a dedicated integrated circuit that is used for speaker protection, and that's the NEC UPC 1237. Now, a common type of equivalent IC is made by Toshiba. So you'll see in one of the other repair videos, it's a TA7317P. Fundamentally, these ICs are custom designed for a specific purpose, in this case for protection for stereo amplifiers. And because it's an integrated circuit, it contains in there all of the different other circuits that normally would be designed around conventional components. So you can see here on pins 1 and 2 within the video for the overview of the block diagram, you can see that these are the sense terminals. So they're monitoring for any high DC voltage, and then in turn what we're able to do then is to provide this output, and then we also have an input then to mute or de-energize, and then most importantly you also need an AC detect. And NAD amplifiers also have this AC detect pin that is used. So if maybe the speaker protection system, say in a NAD amplifier, is not working, it may not be that either pins 1 or 2 is high for speaker protection, high voltage. Actually what has happened is that you're losing the AC signal detect, and that's resulting in the IC not operating. And it has an inbuilt driver circuit, so I don't need to have an external transistor to do this. I can drive directly then from the custom IC, and you can see from the data sheet all of the features around this IC, and they have a broad operating voltage, and you may see these types of ICs that are used for speaker protection systems, but equally so you may also see them in larger power amplifiers where you have a startup power supply, and the startup power supply could use a UPC 1237, and what we have there are over temperature devices like switches which are mounted on the power heat sinks, power output heat sinks, and they just simply operate. So in the event that that occurs, these ICs can be latching or non-latching. So if it's a latching state, it would latch due to over temperature. It would depower the power up startup relay, the large power relay, to depower the main toroidal transformer until such time as the heat sinks then cool down, and then it requires user intervention. So you either have a reset button on the front of the amplifier or on the rear, and it's a simple matter then of just resetting the amp. In some cases it may be designed that the latch circuit is not used, so it just auto resets. So for example, the Pro Sound amplifiers, which are the 800, 1000 and 1600, which I have an example of here for the main power supply which is in the video, that incorporates 2 of these ICs. As I mentioned, one was in the startup, used for the over temperature, and then the other one then is for the speaker protection. You'll also see in the video, I'll just give you a high level test circuit, and this is taken directly from the data sheet. Often when you're fault finding amplifiers, it's really beneficial if you're able to get access to the service data. You know, it just makes the process a lot easier, because at the moment what we're talking about here is a straightforward circuit which is either being used for power protection or it's being used for speaker protection. But you'll see later as we go through the tutorial that on modern day amplifiers they are handling a lot of signal processing relating to different circuit protection mechanisms. So without a service manual or a detailed schematic, it does make fault finding very, very easy. When you understand the operation here of the IC, again it gives you insight. So when you come to do your fault finding, if you understand the purpose of the different pins on the IC, then you're able to fault find more effectively and quickly diagnose is a fault with the amp or is it the protection circuit. What is also common in terms of failure, sometimes on the overview where you see the UPC and you see this test circuit, you'll see a 15k resistor with a 45 volt supply coming in. It is not unusual sometimes to find that one of the feed resistors for the power supply has gone open circuit, or for example the capacitors have gone low or high in value. The video also shows from the data sheet a typical application. So you can see there that we have the what terms the class B outputs. So these are for the left and right channel. Then what we do is we take the center point, which would normally go out then to the speakers, and then the IC is monitoring via pins 1 and 2 any DC offset. And most importantly, sometimes we think about DC offset as being a positive value, but actually it can also be negative, so it can be high or low, and the IC is able to cater for both. And then you can see the output then connected to a relay, and then in turn the speakers are connected. Still maintaining on the UPC 1237, what I've shown here is a real circuit schematic, and this has been taken from the Pro Sound audio power amplifiers, and you can see how this IC has been installed and how it's been designed. What's happened here is exactly what we've already explained. So it is driving directly the output relays, and there's two on the main power supply board, and then what you can see is the feed power supply. And again, on some of the repair videos you will note that it was 15k, and it is a very common source of failure. And then you can also see then the timing components as well. So when you come to fault find, you can refer to the data sheet, and it's very easy then to check which pins are the supply voltage, which one is ground, which pins should be receiving the send signals from the left and right channels, and then most importantly you can quickly identify, is that IC working correctly or is it not. In terms of replacing the IC, just be aware that some of these ICs have really gone obsolete over time, so it's a little bit more difficult to source genuine originals, but they are still out there. The next protection circuit that I'm using as an example is for the Cambridge Azure series, and what I'm showing is the 640A protection circuits. Now I've taken this really as probably an extreme example, maybe in some ways, and the reason why is that Cambridge Audio have something called the Cat5 protection system. And is it complicated? I think if you're unfamiliar with it, it can appear complicated, but once you get to understand what the circuit is doing and how it operates, and then from a fault finding point of view, it becomes much easier then. So when we look at the Cat5 protection system, you can see on the circuit schematic that I've put some arrows on there, and then underneath I'm pointing to specific things. And I mentioned on a previous repair video something which is called a comparator. So I'm referencing here an integrated circuit which is an NE5534, and these are operational amplifiers. Now operational amplifiers are extremely versatile, so it's an integrated circuit, and you'll see them in many amplifiers where they are used for processing in the pre-amplifier stage. So maybe you have an input circuit, and then you go into the tone board for the balance, treble controls balance, and you'll find an NE5534 in there. Depending on circuit design, you can control the amount of gain, so you don't get huge amount of amplification, which would be the case if you didn't have any sort of feedback connected for the operational amplifier. But with the op amp in this example, it's being used as a comparator, and what a comparator is doing is you have what we call VREF or VReference. So this is the reference point, and then for here they're monitoring the output across the speaker terminals, and that is the V actual. So this is coming in, and it should be a nominal value, ideally as low as possible, and then in turn that is then goes to a multi-pin connector, and you see on the right hand side I say status signals are read by the CPU. So via the interconnectors it goes off to the front panel board where the key selection switches are, and on there is a microprocessor, or what we call a microcontroller. And that microcontroller or CPU has embedded firmware which can be normally flashed at the factory to change the firmware, and it's running code. So depending on the status of the pins on the microcontroller, it will implement a particular protection function. And the Cat5, as you see here, has multiple sensing circuits. So the first one is that it's able to monitor any distortion. So maybe the amplifier is overdriven, the Cat5 system would come in and then what will happen is it will automatically reduce the volume control and rotate it anti-clockwise until no distortion is measured. The next, simultaneously, it's also checking for over temperature. So again, it's monitoring the temperature of the heat sinks of the power output stage, and then in the event of excess temperature, it will then switch to protection mode and trigger fault condition. It's also doing short circuit protection. So when you switch the amplifier out of standby mode, what it's doing is it is measuring the resistance across the speaker terminals to check to ensure that it's not a short circuit. So if inadvertently the wire maybe connected had been accidentally shorted, or there was an issue with the speaker's coil, then the amplifier again would initiate a fault condition and will go to protection. The next one is it's doing DC protection, and this is very common. So it's looking for high DC on the speakers. If it measures it left or right, high or low, it will fault and then put the amplifier into protection mode. And then it also monitors the over voltage and over current. What's happening here is, and I'll show you, I refer to V and I. So I is current, V is voltage, and what it's ensuring is that the output transistors, so these are Sankin, SAP, N and P Darlington transistors, it's measuring to ensure that there's no excess current or voltage being applied, so it's keeping them within the safe operational limit. Now when the Cat5 operates, you have a protection LED on the front panel, and on the version 2 you also have the description of the Cat5 in terms of the strobing that you will see when a particular protection mode kicks in. So the LED may flash once and then there is a delay, and then it will then flash again. That typically indicates that you have a DC over voltage situation on the terminals. Alternatively, you may find that the LED strobes 4 times, then with a delay, and then repeats the sequence again. In that case, it may be detecting a short circuit on the external speaker terminals. If there's no issue with the protection system, then it's operating correctly. So what you need to do is to check the input, for example here to these comparators, to verify where the issue is coming from. Also as well, you'll see on this circuit schematic that they're also using transistors in different circuit designs, again to be measuring the different statuses from the different protection circuits. Now with a microcontroller or a microprocessor, it typically operates from a voltage of 5 volts. So this is the first time that you may well have heard this term. What we're looking at is the logic states. So with TTL logic, or transistor to transistor logic, you have 2 states. 0 would be logic 0, off, and logic 1, or high condition, would be typically 5 volts. So what we do here is we just effectively, via the comparators and the transistor switching circuits, depending on the fault condition, we're making it high or low. Normally, low means there is no fault with any of the circuits, but if any of them trigger, then that pin will then go high, and that would be read directly by the microprocessor. The firmware code would then run, and it would carry out the particular operation that was assigned. In some cases, it just de-energizes the speaker protection relay and then will flash. But what is more difficult when you come to fault finding is maybe the protection circuit operates and you only have one common startup relay, and the design is such that that is what will operate. And then it de-energizes the power relay, switches off the main toroidal transformer or power transformer, and that's it. So you can imagine when you're fault finding, and I appreciate for many of you who are listening to this audio tutorial, you're often in that world, you're unable to make any voltage measurements because there's no longer any power applied. Cautionary, and sometimes I get asked the question, can you override the protection circuit? Well, if you look at the Cambridge Azure range, you can if you keep the standby button pressed in, but what you're doing there is you're just simply overriding the clipping circuit, and there's caution around that because you don't want to override it to the point where maybe the audio was too high, it was overdriven and could result in damage. If I take a more complex power amplifier, I'm thinking of like say the Behringer iNuke series, there is a dedicated IC and you see a protection output pin, but remember this is going to be linked to experience, right? So you know, I've been repairing amplifiers for a very, very long time, so you get to know these circuits and how they operate. I would never advise someone to go in there and start to disable a protection circuit. Equally so, I would never tell someone to uprate a fuse in order to determine where there is a particular fault. When I look at power amplifiers, providing I don't have a short circuit in the output stage, which would be very, very easy to fault find with a meter just on resistance, I may in some cases just disconnect an output feed maybe to the CPU. So in the case of the Cambridge, if I believe that it was faulting and maybe one of the protection circuits was operating randomly and it wasn't a fault of the amplifier, I may well disconnect one of the wires to the multi-pin connector for whichever status is high, and that enables me then to maintain the power on the amplifier, go in and then find out where that issue is rather than the amplifier just depowering. You'll also see later on in this tutorial I'm going to talk about something which I often put on a lot of the videos, the curse of the brown glue. And what I'm referring to there, and I'll show you some examples, is during manufacture, for many, many years, manufacturers used a bonding glue, which they used to support what they termed as heavier components, be it smoothing capacitors or maybe circuit boards which were mounted vertically within the main amplifier board. The problem there, and I'll come back to this as well, is that the glue itself goes corrosive and it also goes resistive. And the problem with that is that you get failures of resistors on the protection circuit, even diodes, and you also get intermittent problems, and the Cambridge series is common for this. Sometimes I'll get emailed and people ask the question, you know, this is an intermittent fault, and if you do any form of repair work, intermittent faults can just turn into a complete nightmare. You're literally trying to find the issue, or you're trying to replicate the fault. It doesn't put in an appearance. You send the device back to the customer. As soon as they switch it on, it operates and it faults. This brown glue in the protection circuits causes a lot of issues, and it always causes issues with intermittent operation. Could be that randomly the over voltage protection seems to be operating and there is no DC voltage on the back of the terminals excessive, so why is it operating? You'll see on many of the videos I show you internally, and you can see this brown glue is in there, and what has happened is it's formed a conductive path between parts of the circuit where it should not have been. And that's why the fault protection system is operating, because all of a sudden the inputs to the comparators or maybe the detection transistor circuits are randomly sensing an input voltage which shouldn't be there, and then that signal then is flipping, turning on logic 1, and then is then read by the microprocessor. So just be aware of that. I'd also bring your attention now in the overview video to the Pioneer A10, A20 and A30 CPU, and I also use the word microcontroller. So if you want to use the word CPU for central processing unit, that's fine, but it may also be referred to then as a microcontroller. The reason why I'm showing this example is this is a typical modern day audio amplifier, and the central core here is the microprocessor. So you can see here that we have 48 pins on this IC, and it is a surface mount device, and fundamentally that microcontroller is controlling all aspects of that audio amplifier. So you can see here that they will provide what we term as the read inputs, so it is reading signal statuses coming in, and in turn it will provide digital output statuses. It will also operate all of the LED indication on the front of the amplifier, and if maybe this had some form of visual display, normally the microprocessor would then feed some form of display device, and it could be a dedicated IC, which again would then be providing the feedback or interaction with the user or operator. The same microcontroller not only handles the fault detection, but it will also read directly in the input selection as well. So here you can see speaker A and B. It also shows you, for example, the speaker A, speaker B, LED outputs, any of the input selection. And because it's a microcontroller, there's also a pin on there, or 2 pins on there, which are used for the oscillator, because this will run at a set frequency. It could be 4 megahertz, for example. And this particular microcontroller doesn't run from 5 volts DC, it runs from a nominal 3.3 volts. Now with microcontrollers, the manufacturers or authorized service agents can, if they wish, download or burn into the microcontroller brand new firmware. And typically firmware happens for two reasons. The first one is the manufacturer wants to add some new features and functions, or they may be aware from service information that's coming from the field that there's an issue with the amplifier in terms of its operation. There's something not quite right, and often we refer to that as a software bug. So they will make available then new firmware which can be downloaded into the microcontroller, and often on these circuit boards, it's normally underneath the amplifier via a blanking plate. You'll see a multi-pin connector where they can connect directly a PC, running the new firmware and a loader application, and it will load directly then into the microcontroller. So you can see through this tutorial, really we started off where you have fuse protection, all the way through now to a modern amplifier where you had a dedicated microcontroller. And I'll re-emphasize the point here. When this microcontroller initiates a protection mode, it's providing one output. So it will literally de-energize the power input relay for the power transformer, and you can't go any further. The only good thing with the A10 series is you are able to reset the protection mode by pressing the speaker B and mode buttons together, and the speaker protection relay will then re-energize as the main power relay energizes, and then you probably have about 4 to 5 seconds. So if it was just a soft failure, no hardware related, it would clear out the protection mode and it would run correctly. If there's a hard failure, components, then within about 4 to 5 seconds the amplifier would then switch back to protection mode, and then you would see that as a visual indication. Normally you have a dedicated protection LED like in the Cambridge Azure series, or it could be that the power LED is maybe a tri-stay colour LED, so normally it would be green, and then in the event of fault it would then go to red, and normally the LED will flash to bring the attention of the user to show that there's a malfunction. Now the last slide, or the last part of the video, I'm going to come back to this point about this brown glue and really sort of bring all this to a close. What I'm showing here is a Marantz PM66 SE, and this is the speaker protection circuit. This brown glue is very, very common. You know, I can't emphasize this enough. The number of failures of amplifiers that I see in the workshop, probably more than 60% have issues with this brown glue. And the circuit design here is exactly the same as the circuit overview which I showed you for the dedicated IC. So the video shows the direct in-line package. So this is the speaker protection IC, and then mounted around it you can see a number of capacitors. These are used obviously for smoothing of the supply voltage to ensure no noise, and then also the timing components, and then you have the different resistors. What you see is this brown glue, and it's coating all of these different resistors, and even in some cases it's coating some of the pins of the protection IC. What you have is a fault condition where maybe the protection circuit doesn't operate. It has nothing to do with any other fault within the amplifier. So the first thing you have to do is you have to get rid of that brown glue. So you've got to remove the two main smoothing capacitors. You then have to use a plastic scraping tool to remove it, and please, as I've said previously, use eye protection to prevent it from flaking. And then those components there in the protection circuit need to be replaced. So you have to replace the resistors and make sure that none of that glue is touching any of those by-wire links, because they are interconnecting with other parts of the circuit board. And then what I always do, and I sort of refer back to one of my subscribers, Dave Turner. Yeah, I've done a name check. So Dave sent me a little while ago a message, just say, Gary, you must get through an awful lot of relays. And that's true. I do. I literally get through hundreds of relays a year, and that's because this is just a normal service routine, right? What I don't do is do any sort of repair work and leave those relays in there, because they could be in operation for maybe 30 years. So I know from experience that the contacts will wear, so I just simply swap the relays out for high quality seal type relays, and I keep in stock a very, very broad range, and then just change them out. And the reason for that is, as I've always said before, you want to build some longevity into your repair, but also as well, we know these issues, right? Resistive worn contacts lead to noise, intermittent loss of sound, all of the things that you don't want to sort of deal with during the test phase of repairing an amplifier. You need to take care of it straight away. So really, to close out, I think this has sort of been insightful. Hopefully you've learnt a lot, and if you have any questions or you need any further information, by all means come back to me. What I'll do is I'll look towards doing maybe some other types of videos like this, and not just singly about an amplifier repair, but in connection maybe with a particular circuit. Maybe do one, say, on power transformers, for example, but just really to expand out some of the knowledge base on the channel. And as always, I really appreciate you taking the time to stop by and to listen. So until the next time, thank you and goodbye.